In this video, we're going to wrap up the box bakery example with Jack and Jill making their plain cookies and ice cookies and trying to figure out how we can maximize our profit. So what that means is we have to look at their objective function. Okay, so in each of our linear programming examples, there's going to be some sort of objective function, so something that we can maximize. So in this case, we want to maximize our profit. So typically when I'm writing my objective function equation, I'll just use whatever letter comes from what we're trying to maximize. So in this case, if it's profit, I'm going to write an equation that starts with P equals. Okay. So looking at the profit that Jack and Jill make with their cookies, each box of plain cookies gets a profit of $2.50, and a box of iced cookies is $3. So obviously making iced cookies or selling iced cookies is going to make more profit, but we have three constraints as far as the amount of cookie dough we have, icing, and time it takes to make our boxes of cookies. So looking at our equation for our objective function, the total profit P is equal to $2.50 for every box of plain cookies, and recall that X we labeled as representing the number of boxes of plain cookies. And that profit of plain cookies is going to also include profit of a box of iced cookies, which is $3 per box, and Y represents the number of boxes of iced cookies. So we've got our inequalities representing our constraints, but then we've got an equation representing our objective function. So we can pick any point in this feasible region, our yellow area, including on the lines, because all those are solid lines, and we can plug them in to our objective function equation, P equals 2.5x plus 3y, and that will tell us how much profit we're making. But we want to maximize that profit. We want to have the largest number. So the further we get down towards zero, the less number of cookies that we sell, plain or iced, the less money we're making. So we want to try to get towards the outside of our feasible region. So that's why we're picking our 4 vertices. Okay, so we've got 0, 50. This is halfway, so we've got 15, 50. We've got 30, 40, and 60, 0. So those are our 4 vertices. Those are likely going to be, one of those is going to give us the most profit on our cookies. Well, right away, looking at those first 2 points I have, they both sell 50 boxes of iced cookies, but the second point also sells plain cookies. The first one doesn't. So the second point is clearly going to be more profit than that second point, or excuse me, more profit than the first point. So I'm just going to cancel out that first one. I know that that is not going to give me the highest total profit. So I'm going to go ahead and plug these in to my equation. I'm going to simplify it a little bit. 2.5 times 15 plus 3 times 50. Let's see, can I move these here? Go back. going to rewrite this so it's just a little easier to read here. So I've got, second point was 30, 40, 60, 0. Okay, so for 15 comma 50, my profit is going to be 250 times 15 plus 3 times 50. My second point, that profit is going to be 2.5 times 30 plus 3 times 40. My third point, that profit's going to be 2.5 times 60 plus 3 times 0, because in that case we are not selling any of our iced cookie or plain cookies. Okay, so now looking at our total profit for each one, let's see which one gives us the most profit. Our first point, we end up with a total of $187.50. Our second point, 30.40, gives us $195 even. And that third point is going to give us $150 even. So it looks like this point right here maximizes our profit. It's the best combination of utilizing our amount of cookie dough, our amount of icing, the amount of hours that we have to work, and the profit that we make on different boxes of cookies. So one other thing I want to quick evaluate on our graph is what each of these vertices are maximizing with our constraints. So recall that this first inequality, the blue one, which was here to here, so that maximized the amount of cookie dough. The second one, in green, this maximized the amount of icing we had, which is obviously only for the iced cookies. And then our third constraint right here is the hours it takes to make our cookies. So notice how this point right here is only maximizing the amount of icing we have. We end up losing all of this cookie dough we have here, and then we're not quite working all 9 hours that we have. But we can't go any higher because we have that limit on how much icing we have to make iced cookies. So we can't make more than 50 boxes of iced cookies. This next point right here, well, that's a little bit better. That maximizes the number of hours we can work as well, because we're also making some plain cookies, but we still have some leftover cookie dough there. This point right here, it maximizes the number of hours worked and the amount of cookie dough. Doesn't quite maximize the icing that we have. So there just happens to not be a spot that maximizes all three of our constraints. So when you look at something like this, well, quick look at our last point way down here, all that's doing is maximizing cookie dough. It's not even close to icing because we're not even making any iced cookies here, and we don't maximize the number of hours we have to work. So when you see an example like this, it's likely these points that are in the middle that are maximizing most or all of our constraints that is going to maximize our objective function.